Hello and welcome. This presentation is an introduction to the Rubin Observatory's Legacy Survey of Space and Time, the LSST, and the ongoing process to optimize the survey strategy. The VRC Rubin Observatory is being built on Cerro Pachón in Chile, the same mountain which hosts the Gemini South and SOAR observatories. The Rubin Observatory will house the Simone Survey Telescope, which has an 8.4-meter primary mirror. The LSST science camera has a 9.6 square degree field of view and 6 optical to near infrared filters, UG, RI, Z, and Y. Once construction and commissioning are complete, the Rubin Observatory will execute the 10-year Legacy Survey of Space and Time, the LSST. The LSST will be an optical imaging survey of the southern sky starting in a few years. Both the observatory and the survey are designed to make major advances in 4 core science areas: dark matter and dark energy, the solar system, transients and variable stars, and the Milky Way and local volume. This presentation provides a basic overview of the ongoing process to choose a strategy for the LSST that will maximize science. The core science requirements that the Rubin Observatory and the LSST were designed to fulfill are described in the Science Requirements document, which can be found online at ls.st/srd. The baseline survey strategy was designed to meet these core science requirements. An illustration of the baseline survey strategy is shown here as a map of the sky with regions colored by the number of visits received over 10 years. The Wide Fast Deep survey of extragalactic regions, a total of at least 18,000 square degrees, would receive about 800 visits in total, overall filters, in 10 years. Within the Wide Fast Deep region, there is also a requirement that all fields observed in a given night must be revisited in that same night to enable the discovery of moving objects. The baseline survey strategy includes additional areas as shown in the sky map: at least 4 deep drilling fields, the North Ecliptic Spur, the Galactic Plane, and the South Celestial Pole. This baseline survey is a fiducial strategy that will achieve the core science requirements, but there remain many open questions about how to optimize the strategy to maximize the scientific return of the LSST. Here we list 4 examples of open questions about the Wide Fast Deep survey. The first is the Wide Fast Deep footprint. In other words, how the Wide Fast Deep area should be defined. For example, whether and where to apply limitations based on galactic latitude or Milky Way extinction. Second is the Wide Fast Deep cadence. The term cadence refers to how often fields are revisited, both within a given night and in between nights, the intra-night cadence and the inter-night cadence. Third on this list is the optimal filter distribution for Wide Fast Deep fields. The quality of photometric redshift estimates, for example, can be sensitive to the combination of depths in the 6 filters. Fourth, here we mention the opportunity to obtain colors of moving or variable objects by doing the intra-night revisit in different filters. There are also open questions about the deep drilling fields and the mini-survey fields. As examples, 1, whether to add the Euclid Deep Field South to the existing set of 4 deep drilling fields, and 2, what footprints to use for the mini-surveys, and 3, the cadence and filter sequences to be applied in all of these areas. In addition, there remain open questions about how frequently gravitational wave target of opportunity observations could be executed with the Rubin Observatory without risk to the core science goals of the LSST. To help the science community address these open questions, the Rubin Observatory LSST scheduler team is generating a wide variety of simulated surveys. These are called operations simulations, or OPSIM runs for short. Each OPSIM run takes as input strategy parameters such as area and revisit frequency, generates 10 years of site data such as weather, and then it schedules 10 years of observations. The result is an OPSIM database of simulated observational metadata. To help scientists evaluate these OPSIM runs, the LSST scheduler team built the Metric Analysis Framework, or MAF, a code package that enables the derivation of scientific results from an OPSIM database. An individual metric is a measure of scientific performance, such as the number of detections of a type of object or the 10-year co-added depths in an extragalactic field. The LSST scheduler team has so far generated over 70 different OPSIM runs, and the science community is actively designing metrics to represent a wide variety of LSST science goals and engaging in comparative analyses of the various survey strategies. In order to progress towards a decision about the LSST strategy, the Survey Cadence and Optimization Committee, the SCOC, was formed last year. This committee consists of 10 individuals representing the LSST science community and will stand for the duration of Rubin Observatory operations. The SCOC is charged to recommend specific survey cadences for the commissioning phase, for the early science in the first year, and for the full 10-year survey. The SCOC is charged to consider input from both the LSST science community, including the science collaborations, and from Rubin Observatory staff, in particular, the Survey Evaluation Working Group. The Survey Cadence and Optimization Committee has requested input from the science community in the form of cadence notes about their metric analyses of the OPSIM runs. The call for cadence notes can be found at ls.st/doc-36755 and are requested to be submitted by March 15th, 2021. Further opportunities for formal feedback about cadence optimization will be coming in the future. If you have any further questions about Rubin Observatory, there are a variety of ways to find answers. First, please come back to the VRC Rubin Observatory booth in the exhibit hall of the 2021 Winter AAS meeting, where we would be happy to answer your questions. Second, please feel welcome to visit our online community forum at community.lsst.org. This is the best place to seek answers for questions about the LSST. In particular, the science category has a place to, in particular, in the science category, there's a survey strategy subcategory full of announcements and discussions related to cadence optimization. The contents of our forum are publicly available to search and read, and anyone may obtain an account in order to post questions or participate in discussions. There are a couple of additional resources related to the LSST cadence provided in the sidebar of this slide as well. Third, if you're interested in getting involved in preparing for science with Rubin Observatory, you might like to join one of the 8 LSST science collaborations. The science collaborations are independent, worldwide communities of scientists, self-organized into collaborations based on research interests and expertise. They are laying the groundwork necessary to prepare for doing science with the LSST data products and services, and are open and welcoming to all, especially to students. Joining a science collaboration is a great way to learn about Rubin Observatory. Goodbye and thanks for watching.